I'd like to thank ABS anyway for being the gold sponsor for this. And this is Dr. Keith Pemberton. There's a research fellow in crop and physiology at the Tasmanian Institute of Agricultural Research. We investigate the role and adaptation of forage crops within pasture-based dairy systems. His research program investigates genotype adaptation of lucerne within dairy farming regions. He has been recognised for several national awards, including the 2008 Fulbright Tasmanian Scholarship and Dairy Australia and Ministers Award categories of 2011 DAFF Science and Innovation Awards for young people in agriculture, fisheries and forestry.
Thank you.
Yeah, alright.
Sorry for giving you such a mouthful. But anyway, so this talk is entitled Freezing and Drought. I'll just swap slides. That one, first slide actually doesn't go anywhere. It's called Freezing Out Drought, and hopefully by the end of the presentation you'll get an understanding of what I mean by that. But overall it's going to be about adaptive processes in lucerne, or what I think are the adaptive processes in lucerne to drought, and how its implications on the farm. And just acknowledge my co-authors with this paper, Richard Ronson, Danny Donaghy, colleagues of mine from TR, and also Jeff Molnick, who's a professor at Purdue University in the United States. So I guess we'll kick it off and leads on from the discussion we had before the talk. Why lucerne? Why grow lucerne? And so there's several reasons, and these are just four. I'm sure there's others. Anybody in the room actually growing lucerne or considering growing lucerne, you might have your reasons. But four that I could just think of really off the top of my head was improved diet quality. So it's perceived to be a high quality forage. An improvement in the resource base, so lucerne's used in salinity control is a major one, and also because it's a legume, it fixes nitrogen, so it adds nitrogen to the soil, which improves the resource base and also leads on to the next point, which is reduced any fertiliser requirement. And the major one actually in Tasmania is, and while a lot of dairy farmers in Tasmania consider lucerne, they've got a couple of hectares in the runoff block or something like that, is it extends the growing season. So that, and these two photos I think demonstrate that from two field experiments of mine, where during the 2007 summer drought that we had, and the grass pastures around the plots of ground, not much growth, where the lucerne plots are still green and powering on, those cows looking rather longingly at the lucerne plots, and I had to make sure the fences were strong and good that year to keep the cows out. And I do apologise because I can see a map on my screen where that little circle is, because that's meant to highlight a section of the globe, but you guys can't see it for some reason, so I'm sorry about that. But just imagine the globe, and that actually the circle is highlighting sort of the Middle East and sort of Kazakhstan area. But anyway, lucerne as a species is genetically diverse. It's actually a species complex. Us scientists, because we're a bit toffee nosed or whatever, refer to it as a species complex, not as a species. And it's made up of 8 subspecies, and I'm not going to pronounce them because my Latin isn't that good. But the two subspecies which have been the major focus of cultivar development are subspecies falcata, which is the yellow flowered lucerne, and subspecies sativa, which is the purple flowered lucerne. So, and those two species, or two subspecies, have been the focus of lucerne cultivar development worldwide. There's been a little bit of work with Corellia, but it hasn't really resulted in much actually making it into commercial cultivars. But even though we've only used 2 subspecies within the lucerne breeding program globally, even cultivars are genetically diverse, and that's due to its relative intolerance of inbreeding, and also another thing which is called winter dormancy. And winter dormancy, and we know that we rate lucernes based on their level of winter growth, or winter dormancy, and we rate them on a scale from 1 to 12 now. It used to be 1 to 10, but now we've developed even more highly winter-active lucernes. But so it's just a scale, but winter dormancy relates back to the genetic pedigree of the cultivar. And another map of the world up there, which doesn't show up, sorry, but what we can do is we can actually trace back through the genetic pedigree of cultivars back to actually where the original parent germplasm came from. So that winter dormant cultivars, and you can trace right back to sort of the steppes of Russia, Northern Europe, that sort of area. So very cold, freezing winters. Semi-winter dormant cultivars are generally Middle Europe, so not quite as cold winters. And winter-active cultivars you can trace back to Northern Africa, Southern Mediterranean area on the globe. So, and I guess this picture here really demonstrates the difference between winter dormant and winter active cultivars. This little patch of green on the front is a very winter dormant cultivar, it's got a rating of 1. Where at the back, that dead thing at the back there is actually a highly winter active cultivar, had a rating of 10. It had a rating of 10 because it's dead, because it got exposed to freezing conditions in Indiana in the USA, so pretty cold winters over there. And the winter dormant ones are the ones that survive, the winter active ones don't. And that picture there highlights it, also highlights the height difference that you see between the winter dormants and winter actives in winter. Now Australia, we've focused on more winter active types because of that extra growth that they have in winter. And we haven't needed a freezing tolerance within our cultivars because we don't get freezing conditions unless you're like in the very bottom end of Tasmania or something like that. But we don't. But maybe we do need, or after this presentation, hopefully I will convince you of this, that maybe we do need some winter dormancy within our cultivars.
So that what you can see on these two different cultivars, the winter one and the winter dormant and the winter active one.
Yep.
It's where the crown sets really, no?
Yeah, it's the crown.
It's not only the growth, it's where the crown
yeah,
sets.
so that's one of the reasons why it survives. The other reason is that the winter active ones actually don't have the genetic process or the physiological processes to survive freezing conditions in them, so they're not doing things like increasing the cell solute concentration and increasing extracellular formation. We'll actually get to that in a slide, Robbie. You've sort of jumped ahead. Which is all well and good, I don't mind that, but we'll move on. So when I first started my Liston research program in Tassie, we were really just trying to work out how different levels of winter dormancy grew and performed in Tassie. So we got hold of merit testing experiments from late 80s, early 90s, and reanalysed the data sets based on winter dormancy. And what we identified was that at one location, Forth, which we'll classify as a high yield potential environment for the reasons listed up there, the winter active cultivars did better than the winter dormant cultivars. Where at Cranbrook, which we'll classify as a low yield potential environment, because again the yield reasons are up on the slide, the winter dormant cultivars actually did better. So something's happening here. And so we used just this form analysis, just an ANOVA analysis for those that are statistically inclined, but we also undertook a sensitivity analysis, which is another way of treating the data. And what that allowed us to do is actually classify the genotypes of the level of winter dormancies based on their sensitivity to environment. And this graph sort of shows it. The horizontal line across there at 1, anything above that line is adapted to a high yield potential environment, and yield potential in this case is actually defined as how much, or what was the average yield in that environment, where the stuff below the line is adapted to a low yield potential environment. So, and what this shows, it confirms the findings from presented on the slide previously, is that highly winter active cultivars are adapted to high yield potential environments, where the winter dormant cultivar is adapted to a low yield potential environment. So something's going on. We're comfortable that something's going on with winter dormancy rating and environmental adaptation. But this is done with stuff from the late 80s, early 90s. You want to confirm it with currently available cultivars. So we sort of took 4 representative cultivars and representing each one of those, the broad winter activity classifications, and we grew them in some environments which we thought were high yield potential, low yield potential. We actually used irrigation to control yield potential. So a dryland environment down in the southern end of Tasmania, and dryland environment up in the northern end of Tasmania, and also an irrigated environment chucked in there as well, just to keep me busy with moving irrigation pipes. But what we found was a very similar result. We had the semi-winter dormant, winter dormant cultivars doing better under dryland conditions, and under irrigated conditions you actually had no difference between the cultivars, maybe a slight trend towards highly winter active cultivars performing better. So something's going on, and this also suggested to us that water, and if you remember back from the previous slide, there's a deficit irrigation location versus a fully irrigated location. Water might be driving yield potential. So what we did is we actually pulled out the semi-winter dormant cultivar and the highly winter active cultivar from the field experiment, and we grew them in the glasshouse, exposed them to varying levels of drought stress. And lo and behold, I discovered plants need water to grow. And that's sort of, I guess it's a major finding maybe. Something it's important for us scientists to remind ourselves of that occasionally, because you think, yeah, we'll test drought and expose plants to not give them any water under glasshouse conditions, and you just kill them. But and so our levels of water depths range from 0, no water applied, 25%, which is a quarter of the water requirement applied, right up to the full water requirement applied. And that picture just demonstrates how those